Hello, everybody, and welcome to today's SEDS Online webinar. As always, we'd like to thank you for watching and for our support, oh my goodness, I can't talk today, for our sponsors from the IAS, which allow us to offer all of these free resources, including our lectures, learning tools, field trips. So make sure you're always taking a look at our website to see what's coming up. Also, make sure that you submit an abstract or register for our upcoming student webinar on AI, machine learning, and big data in sedimentology, which will take place on February 25th, as well as our Carbonate Forum, which will take place the 12th and 13th of May. So definitely want to check the website for those details. So today's lecture is by Dr. Charlotte Pretty, who is a sedimentologist at the University of Derby. Charlotte received her PhD at the Kiel University, and her research interests include quantifying and understanding ancient depositional environments and characterization of subsurface with an application to carbon capture and storage projects. So thank you so much for being with us here today, and I'll hand it over to you.
Thank you. Thanks for the introduction. So yeah, the talk that I'm going to run through today is kind of a summary of a lot of the research that I've been doing. So we're going to go basically through a load of dryland fluvial systems, but focusing on how we get all of that data that we collect in the field of all the different outcrops and how we can build different types of reservoir models from that for the application for like CCS or geothermal, for example. So first thing I wanted to start with is I've just got a picture now of the skeleton coast in Namibia. So a lot of my research is focused on interacting environments, particularly in like dryland settings. So here's an example where we have aeolian settings plus fluvial. Now it's important, well, these environments are very important because the deposits of these form quite prolific reservoirs for, well, originally for hydrocarbon exploration, but now for targets for carbon capture and storage too. And when we think of things like aeolian dunes or fluvial systems, we think, oh, that's got a lot of sand. It's going to be a good reservoir. But these systems often interact with each other and cause basically a variety of different scales of heterogeneities that will affect basically your reservoir. So we need to understand how these environments interact and their deposits to understand basically when we put things like CO2 in the ground, where it's going to go, where would it pool under, and how much we can actually store within the subsurface. So my presentation today, we're going virtually to basically the United States of America. We're focusing in like the Southwest, in particular around Utah. So around southern Utah, I'm just going to get my pointer. So around southern Utah here. So a lot of our study sites were near a place called Moab, and we also went down into like the northern parts of Arizona. So where we're looking is basically this region of like the Four Corners states, so where Utah, Colorado, Arizona, and New Mexico will meet. In particular, where I've highlighted in red, this is called the Colorado Plateau. And we did basically several field seasons out there. We collected lots of sedimentary logs, lots of paleocurrents, and what's important for today, we also collected some virtual outcrop models using the drone. So on this little figure here, we have basically all of the outcrop locations in white circles. And then we have 3 of these basically camera locations. So this is where we collected the data for our photogrammetric models. So we have one up near Moab, one down here in the very like southeastern corner of Utah, near a place called Bluff. And then we have one near the border of Utah and Arizona in Kanab. So a bit of information about the physical geological setting on the paleo environment reconstructions for this area. So we're looking at the formation known as the Kayenta. And the Kayenta is a fluvial system. And it has these kind of complex interactions between not only aeolian dunes, but it has two competing fluvial systems deposited roughly at the same time. So we've got one that's sourced in the northeast, so from the ancestral Rocky Mountains, and then we have one sourced from the southwest near the Cordilleran magmatic arc. And these two fluvial systems interact with each other, particularly around this region here. So the Kayenta itself, this is what it looks like. So the Kayenta is Lower Jurassic in age. It's the middle formation of what's known as the Glen Canyon group. And it's this one here between the two yellow lines. So as you can see, it's quite distinctive compared to the over and underlying formations. We've got these ledgy, laterally kind of extensive outcrops that we can see also in this figure here. So there's these laterally extensive sandstone kind of ledges, and that's what's kind of distinctive of the Kayenta Formation. Above and below the Kayenta, we have two aeolian formations. So the lower one is called the Wingate, and it forms these kind of steep cliffs with lots of cross-bedded sand. In like the distal region of the Kayenta, it is called the Moenave Formation, and that's where it starts to get to very distal fluvial to lacustrine as well. And then on the top, we have the Navajo Formation, which looks very similar. We've got these large aeolian cross-bedded sets within it. So we're focusing on this middle unit in here that is predominantly fluvial, but does have some interaction with aeolian as well. So the basic methods of most of our data collection, we have 25 sedimentary logs. We have thousands of paleocurrent readings that were measured on basically a lot of the cross-bedding of the fluvial systems, as well as the cross-bedding of the aeolian dunes. And we're focusing on 3 digital outcrop models, one within the proximal, one within the medial, and one within the distal of the Kayenta's depositional system. So here's just a picture of us in the field on a nice sunny summer's day with our little Phantom 4 drone that we use to collect these models. So the sedimentology of the Kayenta, as I've already mentioned, is very fluvial dominated, and the fluvial deposits are, we can broadly split them up into fluvial channels, fluvial like sheet flood kind of elements, and our overbank floodplain elements too. So I haven't included all of the individual facies because this would then be a very, very long talk. There was 21 facies in total across the fluvial and the aeolian deposition, but I've broadly put them into these 3 fluvial categories for now, and we're going to leave some of the aeolian out in the detailed sets because the aeolian is very typical of what you'd see in most aeolian systems. So the fluvial channel elements are predominantly these large amalgamated, both vertically and laterally amalgamated channels. You can see they're very sand dominated. There's not much overbank or muddy deposits within there, but they form these really laterally extensive sheet kind of sandstones. You can also see them interacting with some of the aeolian elements, and we can get them as these isolated channel deposits. So this is where the fluvial system would have been funneled down the interdune corridors in between the dunes. And then another quite, well, it's fairly rare in some cases, but you can trace these out very over like large lateral extents. But we have these really crudely cross-bedded, like gravel-dominated channels. So these are related to our like gravel bar forms. Other bar forms that we tend to see, we've got examples of lateral and downstream accretion in this figure here. And predominantly, which is similar to most dryland fluvial systems that have quite variable discharge, we get a dominance of these large, laterally extensive, low angle cross-bedded to like planar cross-bedded bar forms. And these are what we've interpreted more of these high discharge bar forms in these fluvial systems. The individual facies, well, the typical individual facies that you would see within these elements. In the top left, we've got our typical conglomeratic basal unit. So sometimes they'll be class supported, sometimes they'll be matrix supported. And then going up, we can get some quite unique features. So here is an example of trough cross-bedded sandstone, but you've got these larger clasts that are lining some of the facets within the cross-bedding. So again, we're in this high discharge, high velocity kind of fluvial system. We get various forms of cross-bedding. Typically, a lot of the cross-bedding looks like this bottom right figure. So we have sets of about 20 centimeters of cross-bedding. Sometimes they're quite low angle, and sometimes you've got the nice sweeping asymptotes as well. Occasionally, in our cross-bedding, we'll get what's called recumbent cross-bedding, where we have basically the tops of the facets get ripped back within the flow. So you get this like almost chevron kind of patterning. And what's quite unique to more, well, for ephemeral fluvial systems, you don't see this too often in many average fluvial systems, is we get mud draping on our cross-bedding. So a lot of people will associate that with deltaic or tidal kind of environments. But because of the change in variability of the discharge, we can get this alternation between sandstone and mudstone too. And then we get other facies like these planar laminated sandstones, and this one in the middle at the bottom, where you kind of get this like amalgamated, very contorted heterolithic kind of facies, where you can see laminations of mud and sand being contorted into almost these folded clasts. The other main kind of fluvial element that we see within the Kayenta are these sheet-like, what sometimes people call sheet flood sandstones. And now these differ from our other channelized elements because these are really laterally extensive, not much erosion, and they are dominated by upper flow regime structures. So cool part about this is that we get to see antidunes preserved. Those are upper flow regime structures. So in this figure here, we can see the antidunes being preserved. We also get these upper flow regime plain beds too. A lot of the basal parts of the units will have mud clasts in. So here's an image of just where we've got these armored mud clasts. So they form similar to ooids, where you'll have like a grain of sand that gets rolled in mud, and then the outside of those clasts kind of picks up larger granules as well. So you get these armored mud balls within here. And we also get some pretty cool supercritical climbing ripples towards the top of these sheet flood elements here too. And the last fluvial element that we see is our overbank elements. So these are our dominant, well, predominantly siltstone. You don't tend to find much of this within the proximal or actually within the medial settings of the Kayenta. You do get a few that are about 5 meters thick within the distal setting, but we do get some cool features preserved as well. So we get some biotubation, we get some desiccation, rootlets, and if we're lucky, we get to find some dinosaur footprints too, which was always my goal during my PhD, was to keep finding them. So what does this look like on a big scale? So I've just got a virtual outcrop model here. So this is from the proximal part of the Kayenta. So the Kayenta is in between these two orange lines here, and we've got the Wingate below at the bottom, and then we have the Navajo at the top. So just to get your perspective of how laterally extensive the sandstones are within the Kayenta and how amalgamated they are, it all looks like just amalgamated sand. Occasionally you get some nice features. So here you can pick out this one in here, an abandoned channel fill. And this is filled with your like siltstone to very fine sandstone. But for the vast majority of it, it is amalgamated sand. Now I'm just going to put a bit of interpretation on it now. We're going to go through this a little bit later in a couple of slides. But basically, the red lines here pick out the base of individual stories in the fluvial systems. Those are our our channels, and the blue and the purple represent our bar forms and accretion. So I'm going to add a log just to look at the sedimentology in detail. So as you can see, as we go through this, we're dominated by cross-bedded sandstones. You get occasional gravel lags. We've got some planar sandstones, few conglomeratic units, and then towards the top with the yellow here, we're going into our aeolian of the Navajo Formation above. So basically what we did with all of that data that we collected was we wanted to put it into a conceptual model of what we think these fluvial systems look like. So dryland fluvial systems and ephemeral fluvial systems in general don't typically look like things that you would see in second year sedimentology when you're taught about braided and meandering systems or sinuous and non-sinuous systems. So we wanted to come up with a model of what we thought a typical system would look like based on our data. So here's a 3D model that I drew. All of the orange units in here are our channels. The slightly lighter oranges are our accretionary elements. The browns in here are the sheet elements that I showed earlier. And then the yellows are our interacting aeolian system. So I've tried to pick out all the detailed sedimentology that we've just gone through, as well as imagining what it would look like if it was in the modern day, so top-down view. So we're dominated by a lot of these cross-bedding or upper flow regime kind of structures. And I've also included an idealized section of a typical log through it as well, where we've got our channel elements, our accretionary elements, and our sheet kind of elements here that have a lot of upper flow regime structures in. So that was an ideal model for this kind of system. But obviously, with all systems, they will change and there'll be a different variety and an amount of elements depending on where you are in the system. So I've included some screen grabs of areas that we took virtual outcrop models and their interpretation from proximal through to distal. So this is the proximal area that was just over the border in Colorado. The top image it's not a virtual outcrop model, but it's sliced together photos of that area in a photogram, like a photogrammetric panel. And the bottom is the interpreted version of it. So as you can see, we are dominated by this like amalgamated channel and sheets. So they're colored the same as they were in the previous images. So the oranges are your channels, your browns are your sheet floods, and your orange to pinky things are your accretionary elements. So lots of amalgamated sand, very little. There might be occasional pockets of what would have been overbank. And we have a varied paleocurrent direction too. As we move to the medial section, so this is down in the very southeast corner of Utah. The scale of this model is so this is where I do have a virtual outcrop model. And the scale of this model is quite hard to kind of get your head around. So you might be able to see just above where the pointer is now, like three little dots. So that's me and my field assistants and partners in the field. So you can get the scale of this outcrop now. But as you can see, looking at the interpreted panel, we still get quite a lot of amalgamated sand, but now we're getting these pockets of overbank between these large amalgamated elements. So we've got a lot of accretion in this model, as well as quite a lot of sheet flood elements too. And then by the time we get to the distal, so that's towards the border of Utah and Arizona, we're starting to get a lot more isolated channels appear. So now we're getting them broken up by lots of overbank floodplain elements. We still get some channels within the distal, but these channels, particularly around the bottom here, towards the boundary with the underlying formation, these are related to the secondary fluvial system that I talked about at the start. But we're dominated by these sheet-like sands. So these are like our splay deposits as well. We've got the upper flow regime structures, and we're getting interaction with some aeolian elements here in yellow too. So what do we do with that kind of data? Well, we interpreted a lot of the virtual outcrop models, and what we did was basically digitize around the edges of some of these elements. So here I've included examples from the channels and the sheet-like elements. So the channels I've highlighted here in green, where we've drawn around them, and then the sheet elements are in purple. And we wanted to get the width to thickness ratios of these. And the really cool thing about I used VRGS for this, is that you can input all that nice paleocurrent data that you collected, and it will give you the true facing direction, well, the true width of that channel, because it calculates your facing direction versus your paleocurrent, so you can get more accurate widths of those channels. But as you can see, as we go from proximal to distal, we're getting a decrease, which is what you'd expect, a decrease in the width of the channels. So this has been normalized to a thickness of 1, so we can compare it. So we're getting a decrease in channels and a decrease in sheet flood widths as we go downstream. We then put those into similar models like I showed you earlier. So we wanted to conceptualize what we thought the depositional system would look like from proximal here through to medial through to distal. Now this is the great thing about geology. It's a very visual subject, and it's always really important to try and draw that model. It doesn't matter if you're good or bad at drawing, it's that conceptual model that will help with your reservoir modeling, which we're going to come on to in a couple of slides. So we have to visualize it first. So this is me visualizing basically the decrease in channels and the decrease in the size and the width of the channels to downstream. So how do we basically put all of that information now into a reservoir model? So there's 2 ways that most people can do it. We can either take that useful information that we've collected from our virtual outcrop models of your width and thicknesses. So that's your geostatistics. So you can take all of that, and then you could build a model, like a box model based on that, and populate it by your width to thicknesses and abundance of those elements that you want to model. Or you can use your interpretations of the virtual outcrop. You can take those horizons and you can use that to create the zones that you would typically have in a reservoir model that you could compare to interpreting a horizon in an outcrop as interpreting a horizon in seismic, for example. And that's the method I'm going to show you today. So this is again the image of the virtual outcrop model that I showed earlier, colored by the different horizons. So orange surfaces through here, these represent the channel body. So that's the extent of the channel belt through here. There's a nice, Amanda Owen and fellow authors did a really nice paper on this explaining this. So the orange is the extent of the channel body. Internal to that, we have story surfaces. This is highlighted in red in this. And those are like the deposits of a single channel. So that includes everything with like the bar forms and everything that's within it. So that's this surface through here. There's also bar bounding surfaces. That's in purple. Those are a little bit harder to see in here, but that represents basically the shape of your lateral or your downstream accreting bar forms. And then in blue through here, those are your accretionary surfaces. So those are your internal surfaces to the bar forms that represent different styles of accretion. And then internal to that, if you want to keep going down the different scales, you'll have your like cross-bedded sets within those two. So what do we do with those horizons? So the way to make a reservoir model from virtual outcrops, I've taken these red surfaces through here. So these are our story surfaces in the Kayenta. And what you can do once you've traced them across your outcrop using, you can use different software for this. You can import them into your reservoir modeling software. So I use Petrel for this. So I've imported them as little points to form horizons in Petrel. Just note that the bottom model is vertically exaggerated, just so you could see the difference in the lines. We then take those lines and we basically extrapolate away from those points and create contoured surfaces. which end up being like your horizon surfaces if you were mapping in seismic. So you have to kind of apply a bit of conceptual understanding to the model. So you look at where, say, the deepest part of the channel may be based on like your Z coordinate in the line and your paleocurrent measurements. So in here, the purples in here represent the deepest parts of the channel. So each one of these surfaces represents each one of the story surfaces that we've imported as points. So you build them up that way. And I've incorporated the fact that the paleocurrent direction predominantly is towards the southwest, which is going into your screen at the moment. And what we do, we populate that with, basically, we do facies modeling. So we populate that with a load of stats, so percentages of sand, shale, whether it's coarse sand, fine sand, and we apply that to each one of these zones that we've created in between those surfaces. We can apply things like trends. So in this case, I've applied a trend where we have coarse sand appearing towards the bottom, like you'd find in a fluvial system with a conglomeratic lags, and then the grey that represents the shale, so we're fining upwards. So I tried to represent fining upward sequences within this. And you end up with a reservoir model with different statistics. So for this example, we have 56% sand, 27% of fine sand, 6% coarse sand, and 10% of shale. So this is a 90% sand system, so we've got really high net to gross. But we wanted to test that across proximal to distal. So we have a proximal model near Moab, which I showed earlier. We have the medial model in the southeast of Utah, which again, I've showed that one earlier. Same with the distal model near Kayenta, near Kanab, sorry. And then we basically added rough guidelines of where we think proximal to distal is. So we think this area is proximal, this area is medial, and this area is distal because of basically sedimentology that we see. So the interpreted proximal model we've already looked at. We're a very amalgamated sand. Here's just some stats about the area. So we're 90 to 100% sand. We're greater than 70% of it is amalgamated channels. And we've got less than 5% overbank. So we took those story surfaces and we built a reservoir model following the method shown in the previous slides. To make it representative across the proximal, medial, and distal, we picked a set size for the models. So these are 100 meters by 100 meters. And we wanted to compare them. So as you can see, the reservoir model that we produced from this is really amalgamated and amalgamated sand, basically, with occasional isolated pockets of shale. And if we move to the medial model, again, this is the one that I showed earlier, but this is the interpretation of it. So we've got a big incision of this fluvial element, and then we've filled it in with different individual channels and accretionary elements. We're here within our larger scale model. So now we're still quite amalgamated and we've still got high proportion of sand, so 70 to 90% of sand. We've got quite a range of amalgamation and 5 to 30% of overbank. So I started off by creating a model the size of the virtual outcrop model, just to show you the scales that you can model these systems at. And it picks out quite nicely that big incision surface through here. But to compare it to the other one, we picked a small section of the same size to show you basically the difference in the internal sediment, like heterogeneity and structure, once we've modelled it. And then finally, when we went to the distal, so we're this part of the model, again, we're still quite high in sand proportion, but this is primarily because we are interacting with aeolian systems, so the sediment that's available is sand. And we're getting less amalgamation now, so we're getting more isolated sand and fluvial units through here, and we're getting a higher interaction with the aeolian deposits. So we created a reservoir model through there, and obviously the bottom half and the top half of this look very different, and that's because of the interaction with the secondary system. So we wanted to split this model into two, so that we have basically proximal to medial, medial and then medial to distal through our models. So the proximal region, again, in total, we've got about 90% sand. Same with the proximal to medial. But despite them having very similar facies percentages, the actual internal sedimentary architecture and geometries are very different. So you can see in the proximal to medial, we're getting these larger, more laterally extensive, fine-grained sand units compared to the model above. So we're getting more heterogeneity in this bottom one, despite having very similar facies. And then the bottom, the next two are that distal model that I've split up. So the medial model, well, the bottom half of that distal model that we're now calling medial because it's more representative of a medial system. We're, in total, like 60, just over 60% sand. And in the bottom model, we're 55% sand. But again, very different lateral extents of these units that we're modelling. So what we did to see what they'd look like, or how these heterogeneities affect basically the reservoir models, we simulated these. We're pushing water through these models, and you can see that it has swept quite fast along these really amalgamated sandstones, and we got pretty high recovery factors, but we could ignore these just because I ran the model a very long time, so these are a little bit inflated. And then we look at the medial and the medial to distal, particularly this bottom one here. You can see that the actual sand, the main channel units, swept really, really quickly. But these units above that represent the like splays, the thin sheet deposits, reduce really, really slowly. So this interaction is really important to note when it comes to injecting CO2, because these really permeable, laterally extensive sandstones are going to sweep the CO2 first. But these little versions of heterogeneity within here can also trap the CO2, and you can end up with multiple different plumes depending on how they interact. So it's really important to note, basically, you need to know the geology of the rock you're putting the CO2 in. It's very important for it. So how do we try and incorporate all of that heterogeneity? It's really hard to put all of that into one model. We don't have the computer power to do it. So we use an style of modeling called REV modeling. So it's basically a multi-scale modeling technique that can incorporate things from a pore scale. So that's you can get permeability readings, porosity readings from your like little tiny perms, all the way to a lithofacies scale, so individual facies, to your associations, and then eventually your architectural elements, which is kind of what I've focused on so far. And we think it's between these two associations, your kind of architectural element scale and slightly internal to that, so your associations too, that the main heterogeneities that could affect a reservoir, they sit within those ones. So to test this, we used some core from the North Sea, and we used a tiny perm to collect permeability readings. We did this at a really fine, a 5 centimeter resolution through typical subsurface channel successions. In particular, we're looking at the Triassic sandstones now because these were quite important for CO2 storage. And we wanted to get representative facies, but also typical channel successions. And we wanted to get them close to core plug readings so that we can compare what was coming out at different scales. So an example of one of the fluvial sandstones we looked at, the red surfaces through here, like on our virtual outcrop models, represent different stories. All of the colours, I know it looks a little bit confusing, represent different facies. So the large circles in here represent a reading that was taken from a core plug, and then the smaller circles represent the readings that were taken using a mini perm. And the colours represent the different facies. So you can see through here, predominantly our sandstones, where our fluvial channel is planar bedded to cross-bedded sandstone. Each one of these stories, fluvial channels within this succession, show a decrease in permeability upwards trend. which you can associate with your finding upwards of basically your channels. But you can look individually at a single story too and find different trends too. So we're going to look at this individual story, which is a couple of, probably about a meter thick, going through a couple of feet through here. And you can see that there's an increase in permeability towards the center of the channel and then a decrease towards the top. So within this size of channel, we probably only have about 30 centimeters of actual good flow zone, so a really high permeability zone within it. But in the same age, well, slightly older Triassic age system, which a lot of people compare these two fluvial systems to be the same. This is through the same well. You get a very different fluvial setting. So again, same 10 meters that I showed you in the previous slide, but that 10 meters covers one channel. Now, this is similar to some of the sizes of the channels that we see in the Kayenta. Again, you can see here there's changes in the permeability, they're colored the same. And we get an increase in permeability towards the center of the channel and a decrease as we go up. But this time we've got a much larger pay zone, a much larger zone that we can store our CO2 in. So how do we then compare, how do we get that heterogeneity into our models? So again, I'm going back to my virtual outcrops like we went through earlier. And I've just picked a 10-meter section through a channel in the Kayenta. I've built the reservoir model the same as the methods that I showed earlier, but this time I've created, the surfaces are created off like accretionary surfaces. So this is one channel, we've got bar forms within it, and these are the surfaces within. This is coloured the same as the permeability measurement. So yellow is representing our planar sandstone, orange in our cross-bedded sandstone, greys are our shales, purples are our conglomerates, blues are our ripple sandstone. I've got it here. I didn't have to try and remember it. So this is a really small scale model. So we've done 100 meters by 100 meters by 10 meters. And the individual cell sizes within those were 1 meter by 1 meter by 10 centimeters. So this is a really high resolution reservoir model that you wouldn't typically use in industry because it's too fine a scale for the size of a field. But how do we put that? How do we scale it up and basically apply it? So we took that facies model, and in a typical industry kind of model, this is on a different kind of estimate, but you'd have put all of this, all these individual facies, there's probably one facies, which is your channel facies, right? So ignore, this would now be one big cell. All of that detail will be crammed into that. So you can see the amount of heterogeneity and detail that you're missing. So to prove that, we then basically added all of our permeabilities in. So this is coloured by permeability based on like a normal distribution for it from our minimum and maximum values of permeability for the different facies. So conglomerates, cross-bedded sandstone, planar bedded sandstone, structureless, rippled, soft sediment deformed, bioturbated, and mudstone. And you can see it's picked out quite nicely some of the different heterogeneities. So if we were to upscale that and put it in a model, the top one here is an upscaled version of the model I've just shown you. So instead of having a cell size of 1 meter by 1 meter by 10 centimeters, we now have 10 meters by 10 meters by 1 meter. And you can see how much detail's already missed just from that. But again, for comparison, from a larger scale model, when all of this is put in as just a normal channel sandstone of a 50 meter by 50 meter by 1 meter cell, you can see the difference in the permeabilities. So, for example, the top one has a horizontal permeability of 20 millidarcies and a vertical permeability of 0.82 millidarcies. Whereas the bottom one, the element that's not including all these heterogeneities, has a horizontal permeability of 37.8, and we applied a scaling factor of like 10% for the vertical. So the vertical permeability is 3.78. So you can see the massive difference in permeabilities when you don't include these internal heterogeneities. To put facts like stats on it, there is, when you include your heterogeneities, there is a 47% decrease in your horizontal permeability and a whopping 78% decrease in your vertical. So this is really important when it comes to modeling the subsurface, the detail that we are missing, basically, and how things won't match what you've been predicted. So this is why understanding the sedimentology, geology of your reservoir is really, really important. So yeah, that's my talk. That's quite enough of me talking. But basically, dryland fluvial systems, they're really important reservoirs for carbon capture and storage, but they display really unique and complicated sedimentary architecture that we need to understand. You can build models which are probably more representative of fluvial systems using virtual outcrop models. And that can help you understand 3D relationships between the different elements, which will help us understand where a particular fluid would flow in the subsurface. So it's really important, basically, understanding the sedimentology is key for basically creating anything that's going to be representative of the subsurface. But yeah, that is me. Thank you very much for listening. And yeah, I'm open to any questions.
All right. Thank you. That was wonderful. So many super beautiful outcrop photos, and your reservoir models were just amazing. So if anybody has any questions, please feel free to post them in the chat. Make sure you share it with everyone so we can read them out and ask Charlotte. And make sure you include your name and where you're from. We already have a question. So this is from Pierce, watching in a little town in Devon. Fabulously presented and explained talk, probably somewhat peripheral to the talk, but did you consider quantifying the nature of the flows that cause these deposits? And if you did so, and if you did, how did you do it?
Okay, so we were trying to look at the different discharges, and I'm currently trying to write up some work at the moment. I've been a bit busy with teaching about how we can quantify some of the channel elements based on their discharge. So there's been quite a lot of work done on quantifying channels based on crossbedding, but as you could probably see through a lot of this talk, a lot of the sedimentology is potentially more of upper flow regime. So I'm now looking at how we can basically quantify some of the channel elements and their reconstructions based on antidune height and wavelength versus crossbedding. But I haven't looked too much at quantifying the actual kind of like discharge or flow, but it's something I'd be really interested in doing.
Very cool. All right, we have our next question is from Daryl in Canada. Did you find any increase in channel sinuosity from proximal to distal?
Yes. So my proximal setting was less sinuous, more typical of, if you want to class it in a system, more braided towards the proximal. My medial part was much more sinuous. So in the medial section, we started to see a lot more accretionary elements. But our distal setting is characterized more by those like terminal splay deposits.
All right. Our next question is from Nosheen in Geneva. Very nice talk. Which modeling technique would you have used in Petrel? Normally, object-based modeling is used for fluvial channels.
Yes. So even though I've basically built in the interpretations from the virtual outcrops, each one of those horizons I used object-based modeling to import the facies. But you could also use sequential indicator simulation for each one of those zones too, depending on basically the information that you knew about the lateral extents of the individual facies, whether you wanted them as a defined object or not. But you could also use multi-point statistics if you wanted to use training images. It's kind of a way of doing multi-point statistics if we were using basically the virtual outcrop model as a training image.
All right, our next question. So many questions. Thank you for your presentation. This is from Anne. Did you model the geometry of the sediments and channels?
Yes. So each one of those horizons is populated by different facies, and those facies are measured from the outcrop. So we got the abundance of them based on our logs. So I went through all the logs in that area, calculated the percentage of cross-bedding that I'd seen in the proximal versus the distal versus the medial, and then mapped out kind of the lateral extents of some of those facies. So that gave me the numbers to put into the facies model inside of the reservoir model.
All right, our next question is from Carol in North Wales. Hi, very nice talk. I missed the beginning of the talk, so sorry if I missed this, but have you looked at the diagenetic differences between proximal and distal parts of the system, which could have an impact on the reservoir quality for your models?
That's a really important point to consider, and it's a lot. We miss it out a lot with our reservoir models. So for the case of this work, I didn't really look at the diagenesis because my outcrop studies, most of it has an overprint of basically a calcite cement. But if I was doing it with the direct application for the subsurface, then yes, including the diagenetic effects is really, really important.
Definitely. All right, our next question is from Joannis. Great presentation. The properties of the bonding surfaces would be important for the modeling. These would potentially act as baffles and barriers to flow. Were any measurements tried to be acquired on plugs drilled perpendicular through the surface?
No, again, that's a really good point. When I was doing different forms of reservoir modeling, we did simulate the models with the bounding surfaces having different transmissibility barriers. So the ones I showed today was basically we let the fluid flow all the way through. But I don't have them on me, but I do have some where we put in a transmissibility barrier to show the effect that those bounding surfaces would have. I didn't have any core plugs specifically across the bounding surfaces, but there is a difference between basically each channel element. So the bounding surface in itself has a different permeability, but also there's a difference in the trends between what's above and below too.
So much complexity in these. Wow.
Yeah.
All right. Well, I think that was a lot of questions. I think maybe we'll start wrapping things up. But of course, I'm sure you're available by email if anybody has any additional questions and things like that. But again, thank you very much for an absolutely amazing talk. Oh, I just got one more question before we go. It just popped in the chat. This one's from Ross in Ontario, Canada. Did you look at the variability between permeability between the lithofacies scale blocks of your field?
Yeah, so we took the different permeabilities at a facies scale, and some other work that I did, but again, I haven't. There's so much that I could have included, but it's quite hard in a short period of time. And we looked at basically the changes in the individual facies and the variability that you get per facies. The most permeable facies that we found in these kind of systems are your planar sandstones, which makes it really important to kind of start to understand these high discharge bar forms, because that's where we found basically the highest permeabilities. So there's a lot of research that could be done in that.
Definitely. All right. Well, on that note, we'll say thank you again. Make sure you guys are checking our website constantly for those updates on the student webinar and the Carbonate Forum. And hopefully everyone has a great holiday break, and we'll see you after the break.